All right. Hello, everybody. There's a loud mic. We're going to get started. Doors are closing. We will be recording this so that your friends and family who can't be here can watch this later. We're going to record the present, and we'll figure out how to put something to sync it with the slides later. Cool. So I'm Jared Russell. This is Tom Bottiglieri and Solomon Chang, and we're going to talk to you guys about what's going on in AI and how it projects into FRC. And I want to start out with why we're here. We're three software engineers in Silicon Valley who've been doing this a long time. And what AI is doing right now is the most transformative change that we've seen in our careers. We want to share what we see going on, what's coming, and we believe that FRC is at its best when it is a mirror of real-world engineering. There's so much inspiration to be had in real-world engineering. We try to bring that back to the program. Also, it's really fun. Yeah. Brief outline. Brief outline, that's right. So we're going to go over some ground rules. We're going to try to establish what we're going to talk about, what we're not, try to get a read of the room's sort of experience level here so we can tailor this the right way. We want to talk about hype. There's a whole lot of hype behind AI. We want to try to separate that from reality and give you a framework to think about what you see or read in the news. We'll talk about the AI toolbox that exists as of today and how we can use those tools for FRC. And then at the end, we have a bunch of case studies, things our team did, things other teams have done this season that shows how to put these tools into action. So to start off with, let me just get a quick read of the room. Could you raise your hand if you've never heard of ChatGPT? Okay, I don't believe you. Can you raise your hand if you've ever vibe coded something? Okay. Now raise your hand if you have swarms of agents and OpenClaw running on your machine right now. Yeah, okay, I knew there's some here. Okay, that's about the mix that I kind of expected.
All right. Did you do two at the same time?
That's right. And plus one. Go. Okay. What this talk is and isn't. Okay, so ground rules. So what we're going to do, we have 45 minutes. So we're going to do a survey of what's going on with AI in the tech industry and go into case studies of how you can apply these things. This is an instantaneous snapshot of the world that exists right now. So Tom and I, many years ago, we would give talks on computer vision and motion control. Those are timeless topics. That theory is evergreen. In this case, what we're telling you about AI is applicable to April 2026. This field is changing really, really fast. If you walk away with one thing from this talk, it's that just because something doesn't work today doesn't mean it won't work tomorrow. This is not going to be a deep dive in how AI works. We're going to cover enough basics to maybe give you some context for why things are happening, but that's a really meaty topic. This is not a complete step-by-step tutorial. We'll show you some of how to get started, but really we hope you're inspired to go off and figure that out on your own. It's also important to say this is not, we don't have time for discussion on AI literacy, ethics, the socioeconomic ramifications, environmental impacts, equity. These are all really deep, important topics. You should talk to your students, talk to your mentors about these things. Kids often have incredible insights and really thoughtful positions on these things. AI is a reflection of the entire society, the entire world right now, good, bad, and ugly, and there's a lot to unpack there. But like I said, we're just going to focus on how we can use it for FRC right now. And lastly, this is not the only point of view on this topic. We are sort of techno-optimists. We're from the Bay Area. We like to use AI. How AI integrates with education is a topic that the whole world is trying to figure out. Why is that? Well, it's because AI is an arrival technology. So LLMs sort of dropped into our laps, not because they came from outer space. People have been working on AI research for decades, but we sort of had these transformative leaps that bypass the traditional controlled adoption of technology, and sort of it's instantaneously embedded itself in the fabric of our systems and processes. It's uninvited, it's fast, so it forces us to be immediately reactive to figure out what we want to do with this thing. Other examples of arrival technologies in our lifetimes: internet, smartphones. You go back further, there's other ones, but yeah, it's a pretty big deal. And when something like this happens, this is called the Gartner adoption curve. You've maybe seen a plot like this before. When some big tech breakthrough happens, we typically see something like this. It gets into the mainstream, and very quickly, people have wildly optimistic expectations about what it's going to do. So headlines like, it's going to cure all diseases, it's going to solve the need to employ people. It's going to grant immortality, right? These are statements that tech CEOs have made because it makes them lots of money. Then we have the drop of disillusionment. We've also seen statements like this. It's a bubble. We're spending billions and seeing relatively little return. There's a lot of hype. And then usually what happens is then the truth is somewhere in between. We find that this technology is transformative. It is incredibly useful. It doesn't solve every problem, and it creates some new ones. But there's a kernel to it, and that's why the progression of technology through the ages has built upon. And what's interesting with AI, because of how this is an arrival technology, we're kind of simultaneously in all these places at once. You can open the New York Times and you can find statements on all these things. So it's a really interesting time. Okay, so let's talk 2 minutes. I'm going to try to teach you everything you need to know about LLMs and what's going on. In a nutshell, LLMs, large language models, are really just autocomplete on steroids. So autocomplete's been around for a long time. You have a sequence of words, the dog sat on. Guess what word comes next? Probably going to be the. Here's other things it could be. And if you keep solving that sequence of predict the next token, you can generate sentences, you can generate books, you can generate images. And then in 2017, there was the first of a series of breakthroughs, something called transformer architecture. The main thing that it unlocked was the ability to solve these nets at large scale in parallel. And it turns out that adding size and adding data made these things work really well. And so today, we have these massive multimodality foundation models that can tokenize images, text, audio, but it's all basically the same tech. It's basically predict the next word, just cleverly applied in a bunch of different ways. And it's worked really well. So this is a Stanford benchmark of a bunch of different ways that you can benchmark the performance of AI. And we can see, like, after 2017, all this stuff just shoots up into the right, where there's the human baseline on these benchmarks is sort of that dashed line. So this stuff works really well. And in particular, coding is a really good killer app for this. Because code is just text, so it fits the paradigm. There's tons of training data. There's GitHub. There's Stack Overflow. Every team here that open sources your code, the LLMs have digested that. And sometimes it composes back to us stuff from our prior year's code, which is pretty interesting. We also have interpreters and compilers that are purpose-built critics that can work with these LLMs, and so they provide feedback. Yeah, you predict that token, but that doesn't compile, or that doesn't pass the test. And then you can use that in closed-loop and training to refine via reinforcement learning the model, or at inference time, when you ask a coding query, Claude or ChatGPT or whatever can go run a compiler in the background and make sure that they present to you something that it knows is right. And so this is sort of transformative. It means that a model that we've all asked ChatGPT a question, and it's usually pretty good, sometimes wildly off. If you have a critic in the loop that can verify that, suddenly your accuracy gets really, really good. All right, so how does this change the software development paradigm? The history of software development is increasing the level of abstraction, right? Back in the day, we had hardware switches, and then machine language, and then assembly language, and then we had low-level languages like Fortran and C. Then we have C++, we have interpreters, we have Python, JavaScript, Shell. And then AI kind of slots in above that level, sort of right beneath the programmer's brain, right? At some point, we're writing software for a reason, trying to solve some problem, and you have requirements, you have a thing that you want your program to do. The AI tools can kind of slot in right there. And so the right way to think about it isn't that it's a new programming language, because it's not. It's not a compiler. It's not deterministic, because programmers' brains are deterministic. It's kind of fulfilling that same spot in the development hierarchy. And so a really useful way to think about AI is you're not typing code. You're giving it a specification of what you want it to do. And that specification can be in English language, which is very versatile. I'm going to go through sort of a snapshot of what AI is currently really good at and really bad at, and then we're going to talk through the details of how to actually use it. And again, this slide in particular is going to be dated quickly. Currently, AI is great for small projects, single-purpose apps or scripts, where it's sort of a small sandbox, it's a well-defined problem, you don't have to worry about global consequences, just say go. It's also great at grinding out tedious things like refactors or optimizations across a sprawling code base, because it doesn't get tired, it doesn't get fatigued, it can just go apply the same pattern recognition through thousands of lines of code if it needs to. It can ingest huge amounts of context about the project in your library, so you can point it at all the Java docs, all your dependencies, and it will kind of memorize those things. And I have a savant-like recall of which functions exist in the CTRU libraries, etc. You can do things in parallel. You can have multiple agents running at any given time, like a team of software engineers, all evaluating different tasks. And it's also actually really good at iterating until the code is correct or the bug is fixed, as long as you give it the tools to know how to do that. And we'll talk a lot about that. Compare that to things it's not as good at right now. Some big picture, high-level thinking about software design and evolution and the cost of maintaining code, especially in a large company or a large code base. It's really subtle. This is really hard, and it's difficult in like a 20,000 person tech company how to figure out how to let AI agents contribute in a way that's not going to slow you down. That doesn't apply to most FRC teams. Consistently figuring out what your intent is an issue too. So you probably read about AI code adding security vulnerabilities or something to open source repositories. Well, nobody told it not to. Nobody told it to guard against that it should verify that it's not introducing new things. And you're sort of at the discretion of what you tell it to do. It's not a replacement for code review. There still are some hallucination issues sometimes. The closed loop cycle of using a compiler and verification does help with that, but it still sometimes happens. And yeah, sometimes it deletes your entire company's code by accident. There's an article from a few days ago where Claude zapped the whole database in 9 seconds. So yeah, you want to be a little safe. So quick recap. AI coding agents, which is what we're going to talk to, they're enthusiastic and they're tireless workers. They are capable of incredible things. They can be overconfident and they can make an assumption and go down the wrong path and go pretty far. They can have poor judgment. They can decide to do something in a way that you just look at and you're like, well, that technically works, but but they really thrive when you collaborate with them. Meaning, you don't just fire and forget, like in vibe coding. If you're actually asking questions, you're actually iterating a design before implementation, talking about what your testing plan is up front, you can get really good results. And they run on tokens. So tokens are the currency of modern AI. Basically, I talked about what tokens are in the context of an LLM. This is the way in which you pay for using AI. It's sort of doling out the power and resource requirements to run AI. So what does this kind of sound like, this interface, these properties? Really great, kind of inconsistent. I think it sounds like an FRC student. Enthusiastic, tireless, they are capable of incredible things. I am surprised every year at the things that the students on our team do. They can be overconfident. 16-year-olds are known to sometimes be overconfident. Poor judgment, yeah, definitely. But they really thrive when you collaborate and you're a mentor and you're getting into it with them. And then the only difference is they run on junk food, right? All right, cool. I'm going to hand it over to Tom to talk about how we enact these things and how to think about the landscape of what exists.
Thanks, Jared. So I'm Tom. I'm another one of the mentors for Team 254. I've been doing FRC since 2002, so it's been quite a bit of time. And as Jared said, this is a very, very interesting time to be both in the FRC, but also just in the technology world in general. So very, very cool. I'm happy you are all here. So what I want to talk about first is what is AI coding? A lot of people in the room raised their hand when we talked about who's vibe coded something. So some of you already know this. So if this sounds repetitive, apologies. It's a broad audience. So basically, this is a spectrum, right? And depending on the task you're doing, you need to pick, or you can pick, a different tool to do it. So all the way on the left side of the screen is what I'm calling sort of surgical interventions, right? So this is, I am in control of the code. I know what the code is doing, me, the programmer. I know what's wrong with it, or I think I know what's wrong with it. We just need to change this one thing, or refactor this one function, or write this one new test. I can go in and say, do this. And in 10 lines of code, 100 lines of code, it's done. I've made my little surgical intervention using the AI to help. But I was the one who knew exactly what to do. I just had someone typing the letters for me. All the way on the other side is this concept of vibe coding. So vibe coding is this term that gets thrown around a lot. But the way I think about it is when you're just sort of trying to get some output and you do not care at all about the steps it takes to get there, right? I'd like to make some web application and it needs to have, this table that has these boxes. I click on this, it pops something up, right? Whatever. Right? I can explain that to the AI, and it can go use whatever method it cares to do all the checks it needs to do in between, and then be done, and I go and I click all the buttons, yeah, that does the thing I wanted, great. This is an incredibly powerful tool. Our team has used this a ton this year for things that would be, I would call it like low stakes. So something where you just need to like prototype and figure out, is this possible? Or I want to mock something up, or I want to add something to my bespoke scouting application, right? Like, it just like sort of needs to work. It doesn't need to serve millions of people, that kind of stuff, right? Like it gives me leverage, and I don't really care about the downstream parts. But what is to me emerging as both the best thing to do in FRC and also what I've been and a lot of people have been using in the industry is this sort of in-between thing, which is what I've put here as spec-driven. So it's a little more high level than surgical. Maybe we don't have the code yet. Maybe we don't even know exactly how we need to make the code change. But we do have very strong feelings about exactly what the output needs to operate as. And we're going to have strong feelings about the way it is built and interacts with existing systems. So this is like where you're going to get a lot of serious work done. And I have a note on the bottom. There's a bunch of tools we can use to do this. And I've sort of arranged them from the simplest, which is like, you go to chatgpt.com, you type in some question, it gives you some code, you copy and paste it in. And then in the middle, there's AI IDEs, so this is like cursor or anti-gravity, where you're looking at the code as your main view, and you've got this little helper off on the side who can interject. Still a code first view. And then on the right, we've got the full agent views. So this is something like Codex or Claude Code, where you really don't care about the code. You're just letting it rip and having a sort of a conversation about what it's doing it. And I would say like those three sort of, it's not a perfect mapping to the surgical spec-driven vibe coding, but it's sort of. So on the next slide, I want to talk more about this idea of spec-driven development. So this is, if you work as an engineer in the real world, this will look very familiar to you. This is not a new process. We are just changing who does the parts of the process. Right? So typically, like in the technology world, if you want to ship something new, the first thing you do is you come up with a set of product requirements. You make some document that people, figure out what does this thing need to do, who are the users, what does it look like, that kind of stuff. Nothing about how you actually build it, just like what are the major interfaces. And then that moves into technical design, right? Okay, we're going to have to add this module here, we're going to have to have this database, here's the schema of how it all works, and people align on that, and then you go and you cut it. So anyway, we can do the same thing with AI and take a bunch of people and parts out of that cycle and just make this way, way faster. So the thing that's really important to take away from this is if you're using the AI tools, the best thing you could do is use this thing that's called plan mode. So if you use Claude Code or Codex, if you're trying to do anything serious, turn on plan mode immediately. And what you're going to be able to do there is talk about the requirements first. You're going to start by saying, okay, here are the things that I want to do, and you're going to have a conversation about refining that. And then that's going to turn into the technical plan, right? So it's going to say, okay, I need to go make this code change here, I'm going to add this interface here, blah, 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 right? And that might take a while. But at the end of this iterative process, right, the agent's going to go and it's going to inspect all the code you already have. It's going to, understand the shape of everything. It's going to come up with okay, to do this, this thing you spec'd out, I'm going to do X, Y, Z. And that's where your engineering brain is super valuable. Your ability to type characters in doesn't matter. Your ability to understand what they do is why you're an engineer and what you've trained to do, your whole life. So anyway, it's really important here that you get to the point where you see this plan, and you should be spending significantly more time iterating and reviewing this plan than you do building the code or testing the code. This is the most important part. So you basically want to get to the point where the plan, it looks very it needs to say exactly what it's going to do, and it needs to do it in the minimum amount of steps possible, right? It shouldn't be doing superfluous stuff. And then you basically hit go, and it goes and it builds a bunch of code, and then it, tries to verify itself. So that's how do you build the thing to start? So the next thing that's going to help accelerate this, and where we found there's a huge, this is really the thing that accelerates you, is this idea of closed-loop agent debugging. So this is you're basically setting up your AI in a cycle to make a change, run it, figure out what it did, and then fix itself over and over and over and over again. So in this circle we've shown here, the first thing you need to do is observe the behavior. So in the FRC setting, what this means is your robot should be logging everything. You need to log as fast as you can, every metadata from every motor, what's the voltage the promoter's applying, what's the current that it's drawing, what command state am I in, just anything you can think of needs to get logged. So then you need to be able to inspect the logs. So you probably need to have some tool that allows you to pull that information out and put it into a form the agent can understand. The agent will then take that information and look at it and say, oh, yeah, this is wrong, right? Like, I know how to fix that. And then it will make the change, and then it will try to run it in a way where it can understand if it made a change. And that's where some tools come into that we were talking about. And then at the end, it'll compare, and it just keeps doing this until it gets the right answer. Right, so to do this, there's a couple of prerequisites at the bottom that I'll go into more. So here is microphone. Here are a bunch of skills that we've added to our code base that we think are super useful. So these are basically like literally, maybe you're familiar with this. This is like literally a text file in your code base in the skills directory or like a skills.md that says, here's how you do a thing. So we have one that is our simulation agent. So this is incredibly important. We basically have made a way to run a simulation of our robot, both teleop and auto, that has, it requires no user intervention, right? So we can program what, like, here's what we want the gamepad inputs to be, here's what the autonomous state should be, and the agent can just run the whole teleop and like get a log and see what happens and just run in a loop. We have a skill that talks about the robot, like, we're a certified dumper that, has this many degrees of freedom, it can shoot the balls out this way, that way, whatever. And then replay testing, this is a really important one as well. So sometimes you don't want to do a full resimulation, you just want to say, if I had this one very exact log, and I were to have this, if I were to have had a code change and the same exact thing happened, what would that code do? Replay is really great for that. You can use, there's a ton of resources you can use, the Advantage Kit stuff has this built in. But this is great because then you can basically iterate on a very specific piece of code, run an old log through and see exactly what would change. And so long as you set the success criteria, it should be good. Game info, that's like, this is what the field looks like, here's where the obstacles are, this is how long the match is, all that kind of stuff. And then log reading is a skill that basically is like, how do you get those .wpi logs into a format that the LLM can understand? So we have some tool that we coded that turns it from a WPI log into a CSV, and there's a bunch of stuff you can use. It'll be in our release at the end of the year. But anyway, so that's the sort of the skills you need to do that iteration loop. So I'm going to pass it over to Solomon now to talk about what we're doing.
Hi, I'm Solomon Cheng. I've been on QB4 for about 10 years now, and I started FRC in 2010. I'll talk now through a couple of case studies and hand off to others. We have many different case studies. The first two will really go in depth, talk really through some of the prompting we did, look at some of the results. But for the other case studies, we'll really just try to show you the results in the interest of time. So the first case study is around what we call tip detection. You can see here on the left, we go surfing sometimes. And essentially what this means is we want to try to detect whether we tip up on the bump or if we tip up on a ball here. And we want to check that we have no false positives when we're driving around, but we also have a lot of really great true positives here. You can see here on the right, we have this graph, we have what we log all the roll and pitch, like Tom mentioned. And what you could do is you could sit there and look through 10s and 20 different logs and try to tune some different parameters. But we decided to try to use AI to do this. So here on the left is the actual prompt that we gave our agent, and here on the right is a very fast forward of what actually ran. I don't want to sort of read word for the prompt, but there are a couple of key words here I really want to double click on. So the first one is autonomous. The agent already knows now what the autonomous period is. We don't have to prompt it to tell us how that works. That's part of the skill description. The next thing here is robot on the bump. The agent needs to figure out where the bump is on the field. We didn't prompt it there. That's a key usage, again, of the game info skills that Prompt mentioned. And then finally, we ask it to verify its findings. So you'll see right now it's actually running for every single log that we had at DCMP, this whole replay. So we're actually tuning different tip threshold for every single log that we have, and it sort of, at the very end, drops out a result. So I'm going to go to the next slide. And this is actually what the end shows. So this here is the actual result from the agent. Essentially, it's like, I went through all your logs, I found the 2 true pauses that you mentioned, and it also has a recommendation. So we originally said, hey, can we try 50 milliseconds? And it said, well, actually, that seems to be okay, but there's actually another case that you may want to consider. And actually, when I was preparing this case example, I actually forgot that we actually also had a tip in Q96. And then I looked at this and said, oh yeah, the agent's actually right. So it's a great example of how AI can try to fix those issues here. And this is actually the table that it popped out. It shows here for every single match that we had, the pose, max, and angle. And of course, in this case, the 96 qualification, which I forgot, we actually had a tip. And it turned out that actually wasn't likely a true positive. This is a great example of where we use replay testing to figure out how to tune an algorithm. Again, having the agent run replay sort of end-to-end. So that was our first case example. And the second one to talk about is a broken auto. So you can see here on our right is a simulation of our auto, which doesn't work. So normally our auto does what we call a first swipe. It collects the balls, drives over the bump here, and it's supposed to shoot here, but it doesn't. That seems like a bug. And so in this case, it's a typo in the code, and we want to ask the agent how to fix it. So you can see the robot in the sim, unfortunately, doesn't work again. It doesn't shoot. So here's the prompt here on the left, which is talking about my agent. And again, I bolded a couple different words here. The first one is understanding scoring 0 balls. I don't have to tell it like exactly how that works, but it's able to understand what does it mean to score 0 balls. We also wanted it to verify its fixes. So going back to the process of debugging, to ask it to verify or fix by also running a couple different autos. And the final wording here to highlight is that for every single time you run a different auto, check that it's non-zero and is able to score balls. So you'll see it here on the right, Gemini or something else here is churning, going back and forth. And this actually is able to run a simulation end-to-end. So it's going to run the sim, find that there's no ball scored currently, try to look at all the code, try to figure out what's going wrong, and at the very end, it will actually rerun the autos without any user input to verify that it fixed the auto and then also scored more than 50 balls. So again, fast forwarding here, this is the actual output that we get from that prompt. And it says here, in your factory, you had a typo. And this is actually correct. So it fixed the mapping error, where the shoot action was incorrectly triggering what we call a passing sequence here. And it also improved the vision sequence as well. And if you look at the next section, it says, I verified it too. I ran a sim with 2 different autonomous routines. I didn't even have to tell it which autonomous routines to run. And you'll see here a successful auto routine. So again, previously remember that it would do what we call the first swipe. The same thing here, it goes to the center, picks up the balls. Well, previously it didn't work, but this time it successfully scored. And not just that, but we also were able to report the exact number of balls that we did believe we scored. And it says here, both tests exceeded the target, and this was the result of a successful fix.
Yeah, I'll just quickly talk about this one. So this is something that I did while I was eating my kids' breakfast. So we needed the ability to simulate going over the bump. We use some off-the-shelf physics simulator for the 2D simulation, MapleSim, and it works really, really well. An open source contribution, but it didn't have the ability to like understand how to go up and over things, which is something that we needed if we were going to, test our robot in autonomous and feel confident that it was traversing the field correctly. So this was more of a vibe coded thing. This was like, hey, I don't really know how this library works. We use this 2D simulator. Here's the GitHub link for it. Help me figure out how to make it work in 3D. And this was in plan mode, right? And I went back and forth with it for maybe, I don't know, half an hour. Like, give me 3 possible ways to do this. Let me give you the pros and cons of each approach. And it came up with a couple different approaches. And like, one of them was like, rip this sim out and like write something new from scratch. Or like use, some crazy 3D rendering modeling system. It's like, that seems like too much. And it kind of, with a couple different solutions, I picked the one that I thought was, going to be the one that was easiest, and we talked through it for a bit, and then it just kind of cut it. We looked at the results, it looked great, you know. So that was like actually a pretty good example of a vibe-coded thing that worked well for us. And the reason why we were okay with that is like this is sort of the simulator, it's not running on the robot. It's going to be pretty obvious if it's not working. And actually, a part of this that is not the title is you can see we actually vibe-coded as well a fuel simulator. So we have a physics simulation running of the fuel on the field and how it interacts with the robots and goes around and stuff. This was another one, pretty similarly, that we wanted to, we were experimenting with an expanding hopper at one point. Now we have a net on our robot, but basically if you pick up too many balls, it gets taller than, we can't go into the trench anymore. So we needed a way in our software to understand if that was happening so that we could write code that, you know, triggers an alarm if we like run into the trench too big in auto or during teleop or something, have the agent understand that. So we were able to build a thing, you know, plan and build a thing that using the fuel simulation and the bump simulation was able to understand how big our robot was, understand where it's on the field, and see if there's a collision there. So that was another cool one.
The next case study is what we call recovery. And so you'll see here in the sim, there's another robot on the field. And so we want to simulate what happens when we run our auto, we hit another robot, how do we recover from that? So we call that recovery. You can see here the green line that's on the ground or the trajectory recovery pose. And this, again, was this iterative pipe process. We knew we wanted to add this. This is all time parameterized, by the way. And what we do is we detect that we were what we call blocked based on the simulation, but also on real life. And we plan a new path, and that's the new line that's drawn. This, again, was all coded with AI help. We got it working in simulation first. We worked up the ability to sim this. We closed looped it, made it work in sim, and then we finally tested it out. So very similar type actions here. You'll see here that the rest of the auto still is able to continue. And this one was very astute.
This one is fun. So we, at one point, we figured our robot has this like little chute that brings the balls up to the shooter. And so we fill up the hopper, and then we noticed like, hey, there's some space in the chute. We could fit some more in there. But we didn't have the like mounting provisions to put a sensor. And we asked our design lead if they could do it, but they were juggling 4 or 5 other things at the time. And it's like, oh, we can get it to maybe next week. It's like, well, we'd like to do this now. So this was a method that we came up with that I think is pretty cool. I'm calling this use a big AI to make a small AI, right? So we're using the agent to help us craft like a very tiny model that's trained on our robot. So basically what we did was we took a video of us practicing, a few videos of us practicing, we captured logs, we went into Advantage Scope, synced them up, and then what we basically did was we just panned through the video until it's like, okay, we've picked up enough balls where like, at this point, it would make sense to stage them. And you don't want to do it too early, because if your hopper is not full enough, you're going to get onesies and twosies in the chute, right? It's not going to be well packed. But if you wait too long, you know, then you're going to look like you're too full and the driver's going to bail out. So you want to do it at just the right time where like the hopper's full enough so that you can fill the chute and pack it really nicely, but still give the driver time to move your balls. So what we basically did was we looked at the video and we said, that's a good time, that's a good time, that's a good time. Like if I had a button, I would have pressed it there, 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 there. And we did, you know, maybe, I don't know, 30 examples of this. And then we asked the agent, like, hey, given this, like, all these logs and these timestamps, like, can you help us build a model that can predict when I would press that button? And it went off, it, again, suggested a few things, picked one, let it go and train its own little internal model. We tried it in replay. It was like, okay, I tried it in replay. It had this success rate, this precision recall. Let me do a few things to fix it in a loop, like made it better and better and better. And it was like, okay, here's the code you can run on the robot. I verified it every day, or replay. We put it on the robot, driver took it out, worked perfectly the first time. We literally never thought about it again. So that was pretty cool.
Yep. So now we're going to transition. So we talked a lot about using AI to actually improve the robot code. Now we want to talk about some of the other things that we can do. A lot of this still involves code, but there's a lot of things that you can use code to improve your team that don't involve the robot. One way that we used AI was in code reviews, right? So we have a large software team, we have a bunch of talented students, they're contributing code. Historically, our pattern has been that students make a pull request to our GitHub, and then we get a mentor to review it just to make sure that we're not going to blow something up. And this means that a lot of times the students are waiting on mentors to have the time to do that. This year we used a tool called CodeRabbit. There are other tools too. GitHub has their own Copilot-based one too, that basically looks at every pull request in GitHub, looks at all the code, tries to find bugs and propose fixes. And our policy was that CodeRabbit needs to review every PR from anybody on the team before we will then have the mentor do the final sign-off. And these are some examples of some of the cool stuff that I found. WPI's command-based framework is incredibly awesome. We use it, we love it, but there can also be subtle bugs. You can have one command interrupting another or requirements issues. And CodeRabbit's actually able to find those and point them out to us and tell us how to fix them. It can also find classic computer science problems like trying to do a quality test on floating point values or just other generic patterns that high school students are not going to know to avoid sometimes. So it provided a lot of value to us. Another one, scripts, bespoke one-off scripts. We love these. These are perfect candidate for vibe coding. They can help you a lot. In case you haven't noticed, this year's game is really rough on your battery and on your breakers. This is an energy management game. This is the hidden meta of this game, is you need to move as many balls as possible without popping your breakers or browning out at the end of the match. So we have this log reading skill, and so we asked AI to build us a Python script to do energy analysis. So after each match, we get analytics like this that help us look at our distribution of energy. There's even more fields to this that we had to cut off, but this has helped us hone in on refining gear ratios, on current limits and load shedding throughout the season so that we can get to the end of the match and still be able to play.
This is another student-driven project where we wanted to understand how fast our auto is. Auto is a really important part of this year's season. And so what we built was this system that essentially overlaid two different videos. So we essentially took a video of one match with one team and another match with another team. And what we used was AI and also computer vision to figure out, A, how to line up the matches, but also figure out how to find the start frame. And you can see here, essentially what that shows us is for a given match, who's able to touch the ball file first. And this is a key part of our pre-match strategy. Figure out what auto mode should we run, what auto mode should we also think the other team might run as well. This was built with AI, and this is one of those off-board things that we mentioned as well.
I can talk this one. Yeah, so we did say we would talk a little bit about scouting. We did try to take all of our scouting data and give it to the LLM and say, who should we pick? And we found that it wasn't very good. And there's a variety of reasons. But mainly, it's as many of you know, if you ask the LLM the same question twice in a row, you may get slightly different answers. And so every time we would run this, it would probably internally be generating some model of what all these fields meant and how to evaluate them and all that kind of stuff. So sometimes we'd be why is this team here? We'd have no way of saying why is team A better than team B, right? We could ask it to give us that, but then I would not recommend in April 2026 trying to do this. But what we did find it very useful to try to build new ways of visualizing scouting data and talking about how we want to architect our system. So we found that the last couple of games it's been really easy to just use EPA, measuring how good a team is. Last year it was how many things can you put on the reef? More? Great. This year is a little more subtle strategically, just being able to score, there's teams who have really high EPAs that if you stick them on a Sun Alliance may not be able to hit that. Or conversely, teams who have really low EPAs or lower EPAs, there's not many low ones in the championship, but who could, if you put them in the right role, would be fantastic. So we needed to find new ways to find these diamonds, right? So we've actually completely overhauled our scouting system between our first event and championships this year. A lot of AI iteration, a lot of talking to chatbots, a lot of passing documents between each other, leaving comments, giving it back to the AI. Actually, one of our mechanical mentors, Corey, decided to scout teams in the pits. He's not a programmer, but he was able to go in and completely vibe code this really awesome pit scouting system that the students get some app that they can put information in, it gets synced to some backend thing. We do AI-based team descriptions and stuff like that. It's really, really cool. But the fact that a non-programmer by trade was able to do this is really awesome. So if you look at the strategy and scouting part, just play around.
Yep, and maybe the last one. So right now, we're not yet at the point where AI can CAD your robot for you. This is not yet really in its wheelhouse. The visual spatial understanding, the understanding of 3D structure, it's sort of at the bleeding edge of AI research, but it's not there yet. This is a statement that probably in a year or two, maybe it'll be very different. That said, we did use chatbots and LLMs quite a bit in designing our robot mechanically. Right, so on the left side here, this is a plot. This is the result of a very long conversation that our team had with Gemini Pro to try to optimize our shot trajectory, right? So we want to have the property that the ball goes in the goal. There's a bunch of you shoot it lower, higher, etc., to get it in there. And we wanted to understand in particular, how robust does our velocity tolerance on our flywheel need to be? Because the more variation we can allow in the flywheel speed, the easier it is to control. Right, and so we generated this plot on the left that basically for different ranges from the hub and different shot angles tells you how many % error you can have with velocity so that the ball goes in, right? So if you're a little high, it'll go further, a little low, it'll go less far. And from that, we were able to derive some requirements on what the shooter system should look like, right? So there's a lot of robots at the championship this year with drum dunkers with flywheels that look roughly like this. At least the way we arrived at this was literally through the conversation with the chatbot, figuring out exactly how much energy we would lose every time we fired a salvo of 4 balls wide, sort of our worst case. What percentage drop in wheel speed could we accept without missing the next shot? And this is what mapped out was this 3.33 to 1 step up to a 1.2 pound flywheel. So a lot of other teams either did the same math or our vibe coding is present on your robot. But it's pretty cool. So, in conclusion, we posted a Chief Delphi thread about this this conversation a couple days ago, and then sort of people started coming out of the woodwork to share the things that they've done too, right? So we shared our things. High Tide posted their tech binder, very cool, very AI generated. Lots of cool tools there. Cool one here in the bottom left. This is 125. Vibe coded something with AI to pack their truck for the championship. Fantastic application of a really hard problem if you ever tried to fit 20 teams into a truck. We can't wait to find out what you guys are doing. The creativity here is really outstanding. I think we've really just scratched the surface of what's possible. For my part, we intend on 254 to when we release our code, we'll release all of our skills, all of our agents, files, etc. We consider that part of the code. It's interesting. This is one of the things that this AI forces. Is that part of your code? If you want to reuse that next year, do you have to open source it? I hope the answer is yes. But yeah, very cool stuff. And we're just about out of time. So final thoughts. We talked about a lot. This is rapidly changing. For me, at least, I want to wax poetic a little bit. The reason I got into FIRST at this point 25 years ago as a student was I thought it was magic to take an idea of I want this thing to do something, and then in real life move atoms, make things move, make balls go into goals. How incredible is that? That with the power of thought, you can yes, there's intermediate steps you got to build something and use motors and transistors and code, but in the end, you did it. And that's why I'm still an engineer, it's why I'm still involved in the program, because there is that magic. That said, when you do something every day for your job, inevitably, it becomes a routine. And I think with AI tools, it feels magical in a way that is incredibly empowering. It's very, very cool. It really taps into that same primal urge to just create. And it's a complicated topic. There are many consequences and ramifications, but I think it's worth exploring. We had a lot of fun this year with it, and I think it's here to stay. And I think what it means to be an engineer is changing rapidly. And so this is the forefront of engineering education at this level, at this age range in the US and in the world. And so we need to ride the wave too. So thank you everybody for coming out. Yeah, we have about 2 minutes left, so I can take a couple of questions, but don't have too much time if anybody has anything. Yeah?
Just a quick curiosity. What do y'all use mostly as your agents of choice?
Yeah, so the question is like, what do you use mostly as your agents of choice? We all sort of use different things. I found that some things are better for different applications. I think the leaderboard for like which things are better is constantly going back and forth. I mean, Claude right now is incredibly good. Codex is very good. Cursor is really good. But you know, next month there could be a new Gemini or a new Grok or like I wouldn't count on that one. But it's rapidly changing. Yeah, and it's more than just the model too. By the way, it's like the tooling of like what's really going on in these coding tools is like they're figuring out how to best prompt the model, like what default skills and context to give it. Like that's part of the secret sauce too. It's not just who is the best model.
I like that.
Is your code for the 3D bump and hopper simulation available?
Is our code for the 3D bump and hopper simulation available? It's not yet. Typically, we after the championship will open source all our stuff. Sometimes that takes a while, but we'll try to be fast this year.
One over here.
How many years have you used AI?
How many years have we used AI for? That's a really good question. I mean, definitely a couple years ago, we started like asking bespoke questions to Gemini. Actually, last year at Championship, there was one night where in our hotel room, me and a couple of students like vibe coded a algae detection system, and then we tested it on the robot the next day. And it seemed like it worked, but it had some quirks, we didn't run it. Later on, when I was testing out the CodeRabbit integration, I sent that pull request up as like the test case, and CodeRabbit me is like, oh, the reason this doesn't work is because you have this transform backwards here. I'm like, damn it. And so, we've been building up to this point, but definitely this year, like, in a way that we haven't been able to. Just simply because, like, December of like last year, I feel like there's a big step change in what's possible with that.
Opus 4.5 on code was like the right. I think we have time for maybe one more. I think I saw it like over there in the end.
Last one.
You said you use AI for scouting. Has that revealed any new insights into how you scout?
The question is, has AI for scouting helped us find defensive robots? And the answer is no. But I will tell you that if you're, I don't want to blow up their spot, but if you're in the division with the sea otters, they're really good. So we love them. So anyway, we'll leave it at that.
All right, we're at time. Thank you, everybody.